Now let's have case number 2. Case number 2 is applicable when d of x, for the polynomial in the denominator of the proper rational fraction, contains an irreducible quadratic factors and none is repeated. To each non-repeated irreducible quadratic factor ax squared plus bx plus c, there corresponds the partial fraction of the form a times the quantity 2ax plus b all over the irreducible quadratic factor ax squared plus bx plus c. Take note, this form is the corresponding partial fraction of the term containing non-repeated irreducible quadratic factor ax squared plus bx plus c. In short, this is only applicable if the proper rational fraction contains non-repeated irreducible quadratic factor. Now, where a and b are constants to be determined, and this expression inside the quantity or inside the parenthesis is actually the differentiated function of the non-repeated irreducible quadratic factor. Now let's have an example. We will evaluate the integral of 6x squared plus 3x minus 2 all over the product of the two factors x plus 1 and x squared plus x plus 1 dx. Notice that this integrand is a proper rational fraction, since the degree of the numerator is less than the degree of the denominator. And our denominator, the polynomial in the denominator, contains two factors, which the first factor, this x plus 1, is a non-repeated linear factor, while the other factor, this x squared plus x plus 1, is a non-repeated quadratic factor. And at the same time, it's irreducible, because we cannot factor these quadratic expressions into a product of two factors. So we will transform this given integrand into these partial fractions. Notice that the first term in the partial fraction is the form that corresponds to a linear factor, while the second term in the partial fractions is the form that corresponds to a non-repeated irreducible quadratic factors. Now we will equate the given integrand or the given proper rational fraction with its equivalent partial fractions. In this case, we have unknown constants a, b, and c. The first thing that we will do in order to integrate this integrand is to evaluate the values of these constants a, b, c. To do that, we will multiply both sides of the equation by the uh, expressions in the denominator. The purpose is to get rid of or to eliminate those factors to solve for A, B, and C. Okay, so let's start with evaluating the expression on the left-hand side of the equation. Okay, so we will eliminate the factors x plus 1 and x squared plus x plus 1. So what remains, we have 6x squared plus 3x minus 2. Now let us evaluate the expressions on the right-hand side of the equation. So first, we will multiply the factors to the first term in the right-hand side of the equation. Notice that we can eliminate the factor x plus 1. So what remains, we have the constant a times x squared plus x plus 1. How about if we multiply the factors to the second term in the right-hand side of the equation? That is correct. We can eliminate the factors x squared plus x plus 1. And then we will distribute this factor x plus 1 to the first term in the numerator and to the second term in the numerator. And so we get this. So 6x squared plus 3x minus 2 is equal to the product of a and x squared plus x plus 1 plus the product of b and the factors 2x plus 1 and x plus 1 plus the product of c and the factor x plus 1. Simplifying further, applying distributive property for the first term in the right-hand side of the equation, applying the famous FOIL method, and then apply distributive property. And for the last, or for the third term in the right-hand side of the equation, we'll apply distributive property. Doing those operations or required operations, we get this. So we have 6x squared plus 3x minus 2 is equal to ax squared plus ax plus a plus 2bx squared plus 3bx plus b plus cx plus c. And the next to this is we will group like terms, or we will associate like terms. So we get the quantity a plus 2b times x squared. Since these terms are like terms, they are of the same degree, they are of the second degree, plus the quantity a plus 3b plus c times x, because these three terms from the previous step, they are like terms and they are of the same degree, plus the quantity a plus b plus c. Continue. So having these equations, we can equate the numerical coefficients of the expressions in the left-hand side of the equation to the numerical coefficients of the expressions in the right-hand side of the equation. we equate the numerical coefficient a plus 2b to 6. Why? Because they are of the same degree, x squared and x squared. So we have a plus 2b equate to 6. So the same thing goes with the second term. For the numerical coefficients of x, we will equate a plus 3b plus c, which is the numerical coefficient of the second term in the right-hand side of the equation, to the numerical coefficient of the second term in the left-hand side of the equation. So we have a plus 3b plus c equals 3. So we have this. Lastly, we have a plus b plus c equate to negative 2. So we have a plus b plus c equate to negative 2. The next to this is we're gonna eliminate, we're gonna use elimination method here, as I have mentioned in the previous case. We can use either elimination method, we can use substitution method, or even we can use matrix algebra to solve for the unknown in the systems of equation. But in this case, I'll make use of the elimination method. So I'll deal first with the first and second equation, that a plus 2b equals 6 and a plus 3b plus c equals 3. Now here, I'll try to eliminate the constant a. Actually, it depends on you if you will eliminate first constant b. In this case, I'll eliminate constant a. So to eliminate the constant a, I'll multiply negative 1 to the terms of the first equation. So we have negative 1 times a, and negative 1 times positive 2b, we have negative 2b, negative 1 times positive 6, we have negative 6. And then I will add this derived first equation to the second equation. And so I will eliminate the constant a because they are opposites. So negative 2b plus 3b is positive b, copy plus c equals negative 6 plus 3 is negative 3. By the way, you can multiply negative 1 to the terms of the second equation, and then do the same process as I have shown. If you correctly apply the process, I am 100% confident that your answer and my answer is the same. Okay, so now I'll deal with the second equation and the third equation. So since I eliminated constant a in the first process, the same process will also apply to this. I'll try to eliminate a here. So I will multiply -1 to each term, sorry, of the second equation. So I have -1 times the quantity A plus 3B plus C equals 3. So I get -A minus 3B minus C equals -3. And then I'll add this derived second equation to the third equation. By the way, this -A minus 3B minus C equals -3 is still the same with the original equation A plus 3B plus C equals 3. Because the equation remains true even if you multiply any number, any real number to each term of the equation. And so let's continue. Now I will add the terms of the second equation to the terms in the third equation. Notice we have -A in the second equation, +A in the third equation. So these guys will be eliminated. And also we have here opposites C, -C and +C, and these two will be eliminated. So what remains? We have -3B plus B, which is equal to -2B, and we have -3 plus -2 is equal to -5. Solving for B, we have B is equal to 5/2. Now since we already have a value for the constant B, which is 5/2, we can actually solve for C by substituting 5/2 to B. Doing this, we get the value for the constant C. C is equal to -11/2. Now having these values of constant B and constant C, we can solve for the remaining constant, a known constant, A. But actually, we can substitute these 5/2, which is the value of B, and -11/2, which is the value of C, to any of these equations. I'm 100% confident that we substitute this 5/2 and -11/2 to the first equation, the answer is equal to 1. If we substitute this 5/2 and -11/2 to the second equation, I am 100% confident that the answer is A is equal to 1. The same thing with the third equation. And so we have the values for the unknown constants A, B, and C. We'll use these constants to substitute to the unknown quantities A, B, and C. And so we have the integral of 1 over x plus 1 dx, where 1 is the value of A, plus the integral of 5/2, which is the value of B, times the quantity 2x plus 1, plus the value of the constant C is -11/2, all over x squared plus x plus 1 dx. By the way, this quantity, this expression inside the quantity, this 2x plus 1, is the first derivative of the non-repeated irreducible quadratic factor x squared plus x plus 1. Okay. What happened here is we just separated the terms in the numerator since they are of the same denominator. So we separated them. Then we will apply integration of product. So we have the integral of dx over x plus 1 has 5 halves, which is the numerical factor in the numerator. We have 5 halves times the integral of the quantity 2x plus 1 all over x squared plus x plus 1 dx minus 11 halves times the integral of dx all over x squared plus x plus 1. So we will integrate each terms separately. For the first term, this is integral of dx over x plus 1. The first term we can apply theorem 13. Theorem 13 under integral of logarithmic functions. While for the second term, what do you think? Do we have a standard formula to evaluate the second term? Yes, we have. Actually, we can use U substitution here. By the way, when can we use U substitution? We use U substitution when the examination of the integrand, if we let one expression or one factor of the integrand or one quantity in the integrand to be our u, or to be the value of the variable u. And then when you derive this u with respect to the, say in this case, with respect to x, if that derivative of u with respect to x is present in the remaining quantities or expression of the integrand, then U substitution is helpful. Now in this case, I let U equals the expression in the denominator, which is x squared plus x plus 1. And then I will differentiate this U with respect to x, so I get du is equal to the quantity 2x plus 1 dx, in which this 2x plus 1 dx is the remaining expression per quantity in the integrand. And so I use U substitution here. Solving for dx, we get 1 over 2x plus 1 du. How about for the last term? Do we have a standard formula to evaluate this integral? Yes, we have. Notice that the denominator is a quadratic expression. And we already discussed this, how to integrate integrals containing quadratic expression. We will use completing the square method. After using completing the square method, we will decide as to what standard formula is applicable to transform the integrand and to evaluate the integral. So in this case, I let the function of x equals x squared plus x plus 1. Now we'll apply completing the square method. So we have x squared plus x plus 1 over 2 raised to the power of 2 plus 1 minus 1/2 raised to the power of 2. But wait, let's have a review. Where did I get this 1/2? Where did we get this 1/2 raised to the power of 2? The method of computing the squares states that in order to express the quadratic expression into sum or difference of squares, we will get half of the numerical coefficient of the second term. Now our second term here is x, and the numerical coefficient is 1. Half of 1 is 1/2, and then square. We have this. Then we will add this 1/2 raised to the power of 2 and subtract this 1/2 raised to the power of 2 to the last term of the quadratic expression. And then we can express this quadratic expression as sum or difference of two squares. This is our first square, and this is our second square. So we have the integral of dx over x plus 1 plus 5/2 times the integral of du over u, because 2x plus 1 dx is our du, and x squared plus x plus 1 is our u, minus 11/2 times the integral of dx all over, oh, I'm so sorry, never mind of this equal sign. This is a typographical error. Sorry for that. Never mind of this equal sign or equal symbol. Supposedly it's not part of the equation. Okay, so dx all over the transformed form of the quadratic expression. We have the quantity x plus 1/2 raised to the power of 2 plus 3/4. Now recall theorem 13. As I have mentioned a while ago, the integral of du over u is equal to the natural logarithm of the absolute value of u plus c. And theorem 23 states that the integral of du over a squared plus u squared is equal to 1 over a times arctan of u over a plus c. Theorem 13 is applicable to the first integral. Theorem 23 is applicable to the third or the last integral. Oh, here comes again this equal sign. Never mind of this equal sign. It's a typographical error. Sorry for that. Now applying this, by the way, for the second integral, this is, yeah, we can also use a theorem 13 for the second integral. Actually, theorem 13 is applicable to the first integral and the second integral. Now applying this standard formula, we have the answer. So the integral of 6 squared plus 3x minus 2 all over the product of x plus 1 and x squared plus x plus 1 is equal to our answer. We have natural logarithm of the absolute value of x plus 1 plus 5/2 times the natural logarithm of the absolute value of x squared plus x plus 1 minus 11 over the square root of 3 times arctan of 2x plus 1 all over the square root of 3 plus c. Now in this lecture, I use these two references, Differential and Integral Calculus by Feliciano and Toy, 1983, and Calculus with Analytic Geometry by Peterson. Now, I also have here suggested online readings for further learnings. Thank you for listening. Stay safe and healthy. This is Sir Pao.